This is my small but fairly capable CNC machine that I designed and built. The machine is working and capable of multi-tool operations and cutting aluminum, the material I sort of designed it for, quite well. But the CNC has seen less use than I like, and wanting to start the first bigger project with it, I want to fix some of the smaller things that would make a large project quite a lot more difficult. These are primarily the alignment of the axes and this unfinished enclosure, but there are also some smaller bits like the half-finished oiling system and the ripping of the way covers. So while working on fixing these issues and therefore having to partially disassemble the machine, I want to review my build and show what worked for me and what not so much. Some of the dimensions and key features of the machine are the travel in X 340mm, in Y 240 and in Z 150mm. All axes can go close to 2 meters a minute, but they only usually go up to 1 meter a minute to reduce the load during fast motions and not lose position. The spindle is a generic water-cooled 24,000 RPM 1.5 kilowatt spindle with an ER16 collet system, which is run with a second-hand Toshiba VFD. The controller is running Linux CNC on an all-in-one PC with a breakout board using the 36-pin analog output, so control-wise it's about as low-tech as you can go. And finally, the cam is generated using a modified G-code output in Fusion 360. So the machine basically consists out of 4 parts. The heaviest and also the base is the Y-axis on the bottom. On top of that sits the X-axis, which is quite a bit thinner, so that the Y doesn't have too much weight. And then you have the third component in the back. That also is the Z-axis, which then connects to the spindle and all its components. All of these are cast from epoxy granite and have lasted really quite well. This was the first project that I completely designed in CAD beforehand, and is still to this date the largest project I ever designed in CAD. I modeled the parts that I can buy, like the linear guides and rails, and the ones that I cut and built separately. But the resulting shape of the epoxy granite pours were then modeled in the master file. This is not the cleanest, but it worked really well for this project, as I had little fixed points or reference material that I was working off. And I will put the 3D files to access on my GitHub. For building the components of the CNC, I chose epoxy granite, or in my case mineral epoxy, as it seemed an interesting material to work with and it did not need any specific tools that I could not build myself. Before going into the build, I want to show you some of the multiple test runs that I did to find the optimal mixture ratio for the components that I used. When going for this mixture, I had 2 goals in mind. One, to use as little epoxy as necessary, also to reduce cost, and use as much of the coarse material as possible so that the area that needed to be wetted during mixing is reduced and there's a less chance of entrapped air pockets. For the epoxy, I did not buy anything special, but one with at least 60 minutes of open time. This was important as I would be mixing in batches. With the long open time, there will be also a long curing time of at least 32 hours. But this would be beneficial as the castings are up to 8 centimeters thick, and otherwise it is possible that the heat builds up within the part. The only downside to that is that you need to wait for at least 2 days for the part to be fully cured before breaking out the mold. For the solids, I used a mixture of large particles, medium particles, sand, and really fine sand. Later on, I also added some pigments to get an even color. These pigments were meant for coloring concrete and work quite well with the epoxy. For the trials, the epoxy and stones were stirred by hand and then poured into wooden molds lined with parchment paper. The paper made the demolding quite easy. At this stage, no vibration period was included, so there were always some air pockets. I did about 13 test runs, starting with only 5% epoxy and way too much coarse material, to over 10% epoxy and adding mostly fine particles into the mix. It was quite difficult to break some of these test pieces, but I managed it by holding one side in a vise and then hitting the other side with a hammer quite hard. I want to highlight 3 parts. The first one having not enough epoxy, second one having not enough fine material, and the third one having too much epoxy. The first one has actually a really nice surface, but there wasn't enough epoxy so that the fine particles can flow into the voids and fill it out completely. The second one is quite obvious. There wasn't enough fine particles or epoxy to fill out all those holes. The third one looks quite nice. Here on this side you only see the holes from the air bubbles, but you can see the top surface is really quite shiny, indicating the excess of epoxy. One interesting finding for me was that when I increased the epoxy content to over 12%, it made working with the mix a lot more easy. This is also why I ended up with 14% epoxy and 86% solids in my final mixture. This means that there's always an excess of epoxy that forms on the top of the part, but also makes working with the mix a lot more easy. The amount of pigments is not included in these percentages, as I noticed that less than 0.5% by weight is more than enough to color the entire mix. So in the end, the solids are made out of 8% coarse, 20% medium, 24% fine sand or sand, and in large part 34% of the really fine material. All axes are similar in the fact that the external components and other casting get connected to him with these aluminum fixtures. I prepared those fixtures by printing out drilling patterns and then started to drill and tap many holes. After finishing the base CAD design, I got some pre-cut plywood from the hardware store to mock up how this part will look like. For me, a model showing that something is 8 centimeters thick does not really convey how it will look like in real life. After a couple of tweaks to design, I got some 18mm laminated plywood, also pre-cut. From those pieces, I then started to build up the actual mold. For cosmetic things like these bevels, I couldn't use laminated wood, so I used untreated instead. I put some construction adhesives on top of them to close up the pores and then used candle wax as a mold release. Some parts were really quite stuck though, especially the lower pieces and where the motor sits. Here some actual mold release would have really helped. Here I have placed the moving parts on the underside, sort of where the epoxy will live. This is done to align the fixtures and make sure that the moving parts will move freely after pouring. For the linear rails I used 10mm thick plate that are fixed into the casting along their entire length. For the ball screw I used 5mm thick plate, and these ones are primarily fixed into the epoxy where the bearing housings sit. To connect the different castings to each other I used 10mm thick aluminum plate. I got these pre-cut from eBay as I used sort of standard sizes like 25 by 15 or in other cases 20 by 25 centimeters. This also really helped with the cost. To fix the aluminum parts into the epoxy I used a bunch of screws that stick into the casting. The remaining holes that would be needing on the top side of the casting I blocked off using tape. With this sort of build you won't achieve micrometer accuracy, but it is doable without any fancy tools. Next to my now retired drill press and my bandsaw, I used some basic hand tools. From the volume of the CAD model I was able to estimate the amount of material needed quite well. For the y-axis here we used a combined 45 kilograms. The epoxy was mixed in smaller containers to make sure the binder got everywhere. Once that had happened it was mixed with the dry components. As we mixed in a 10-liter bucket, multiple batches were necessary. Here the long open time really came in handy. In the best case you would degas the mixture before the pour, but I would need quite a large vacuum chamber. So I made myself a vibration table out of a motor with an off-center weight and a piece of plywood, as well as an old bicycle tire. This got a lot of the air out and I did not have any problems with inclusions. While curing, the mold got warm, but I would say not more than 30 degrees centigrade. As mentioned before, this is the y-axis and also the base, which was now cast more than 3 years ago, and I already had to move the machine once. So it's great to see that there are no cracks forming and or pieces missing. The mold on the side was quite easy to remove, but the lowered features, especially where the motor sits, were quite time consuming to clean up, and at a certain point I just let it be. This was the first large casting and it worked out really well. There are little air pockets here and there, but nothing major, and I can almost use every of the tapped holes. I think I forgot to tape off maybe 3. The y-axis was sort of the easiest part, as it has only one reference surface, which is the top. The z-axis and the second casting is in that regard a bit more difficult, as it has to align on the top and also on the side, which is now the bottom. That worked okay-ish, but the resulting angle is not a perfect 90. This part also has some additional features, as the step on the side with 3 through holes each that connects this part to the base, and there's also a step on the back that reduces the amount of material that is needed during casting. Those additional features worked, but made the part a lot more difficult and the surface on the back quite rough. For this part, about 30 kilograms of the mineral epoxy was needed. Because of the step, there was a longer vibration period in the middle. To pop the air bubbles, I also used a hot air soldering iron, but the air trapped under the cover that forms this step didn't really have a chance to get out. It is interesting to note that it was beneficial to change the speed of the motor during the pour. To get the mixture to flow, a slower speed and therefore vibration frequency was more effective. And to get the air bubbles out, a higher speed was better. The smaller parts are the x-axis and the spindle standoff, with about 8 kilograms of mineral epoxy each. With the x-axis, my desire to build a compact machine really quite got to me. The part is stable enough, but there are some obvious holes and defects. But as I did not see any excessive vibration and or flex during use, I think it's fine. To help with alignment, the plates for the lead screw and linear rails sit on fixtures that connect these parts to the y-axis. This means that there are small pockets that need to be filled during casting, and as you can see, this did not work. Also, when looking from the side, the plate with the lead screw sits quite low. So low that some of the screws which hold it in place poke out of the bottom. The assembly starts with the base, and this also then sets the first plane to which the other axes have to be aligned to. The sort of assumptions that I will take are that this is an actual flat surface and that the y-axis is moving in a straight line. Especially with the straight line part, I'm not fully convinced, as I did not fix these linear rails as they're supposed to be. As you just saw, I played around with this contraption for a bit, and after a bit back and forth, I got it to within a couple hundredths of a millimeter. But I would not count so much on absolute values. As mentioned, this build isn't about high accuracy, but I still want to put in some effort to make it as usable as possible. the x-axis, now all the major parts of the machine are back together. But this is also the most annoying part, as there's barely room for my hand under the casting. The parts align quite nice, and I think it's a lot better than before, but we will see when I mill the first part. Next then is to finish up the wiring and then continue with the enclosure. This is what it looks like with all the wires back on the machine. I have here sort of the main bus, all the cables that come from the control cabinet, and it then branches off to the different axes. For example, this is for the y-axis, motor and end stop, Z, and all the way back down here to the y-axis this way. I'm trying these sort of cable housings where I'm expecting a lot of chips to build up or to fly by to hopefully protect him a little bit. The next step then would be to put back the weight covers, but afterwards you won't see any of this. So the cabinet is aluminum extrusion construction with some laminated plywood on the inside, so I can wipe it down and try to keep it clean. Right now here's just the void that I want to fill up, probably with some insulation, also to reduce some of the noise, but mainly to fill up this void and then block it off also from the outside with something, so to make it a bit more clean and more completed look. Right now I'm sort of planning on the door, which will be also aluminum extrusion with some hinges at the top to then also receive a window. So this is what the enclosure looks now with the door in place and the electronics enclosure already on the side. I want to fix the monitor and keyboard on this mount, but otherwise everything is sort of in place. I ran out of T-nuts, that's why I sort of just taped these into place at some spots, and I don't really have something to keep the door open at the moment. I want to do something with gas springs, but I will first want to check if I like the design and the functionality of this box, and then sort of finish it up. With the rest of the electronics mounted, all the machine parts are back together. I haven't really gotten into the electronics, as this will be the topic of the next video. And to see if the effort was worth it, I will start with some test cuts. I wanted to start by surfacing the T-slot table, and I'm really glad that I did. As you can see, the cutter touches at the very edges, but there's probably a bow in the middle where you don't see any material removed. So this is what it looks after planing. I think I took off maybe a mil in some places and less in others. To try to compare the before and after, I took out some test pieces. This one is for showing the flatness over the surface. I can feel, and you can probably maybe also see it on camera, there are some obvious ripples in the surface, and if I put a sort of straight edge on near to it, there's some quite a bit of light shining through it. This part then was after reassembling but before planing the T-slot table, and yeah, you can still feel, and then you can also see some unevenness. And this one, it is smaller than the original test piece. You can still see some evenness, but this could also be the cutter. But it feels better, not perfect, but better. And also, if I put the straight edge, it's less. You can still see a bit of light, but I mean, it's a 20mm cutter, and it's a hobby machine, so I'm really happy with that. Also, this is one before. The X and Y alignment before was quite well. I can barely feel any play if I try to wiggle along this angle, and this one was done afterwards. And also if I place it here, I can't feel any play at all. And overall I think I improved it a bit, and well I take it. This is a trial part for an upcoming project. It will be machined on both sides and has one pocket as well as 4 holes. I like to touch off the part with a smaller tool and then start the surface operation with a 20mm insert tool. You can see an offset with a bearing and a machine part on top of the tool setter. This is to incorporate the larger 20mm insert cutter that I use. This is for sure a temporary solution until I find either a larger tool setter or a better setup to incorporate the larger tool. Okay, I think we will try this again. I believe the spindle didn't have enough time to really spool up to get the target RPM. So this is the test piece. It turned out okay, I would say. I'm just happy that it worked and that I could do the multi-tool operation. The only thing that didn't work was the spot drill part. I haven't set up the tool setter just right, so this hits off center and then it has to tilt, or the offset that I included tilts. This offset is included because this is a 20mm cutter and the tool setter is just, I think, 12mm, so I need something that can incorporate the large cutter. I like the large cutter because it removes the material quite efficiently and quite silent. You can just let it run. It's not too annoying. The same with this end mill. It's a free float, 6mm end mill, and the helix is I think 45 degree or maybe even 50 degree. So this high helix then ensures that there are always two flutes in contact when I do the milling. As you can see from the parts in the back, this part took quite some trials and I'm still not too happy about the G-code. Yeah, I'm just learning and trying to figuring out, but otherwise worked. Overall, I really enjoyed working with minimal epoxy as it gives you good parts without any fancy tools, and you don't have to worry about volume contraction as you would do with concrete. I think the quality of the parts could be improved even further by upgrading the vibration setup and or even including a vacuum pump. So far I had no issues by using the combination of aluminum inserted into cast mineral epoxy, and as I've seen also commercial products use that combination, I think that's fine. And with the aluminum I also don't have to worry about oxidation. The cast parts altogether weigh about 100 kilograms, so with the aluminum and all the moving parts I would say the entire machine weighs something between 150 to 180 kilogram, which gives quite a sturdy base for the milling that I intend to do and the parts that I need. The overall design is quite compact, which I like, but that also leaves limited space to work on. And the Z height is actually quite limited, so I think I will need to install a riser block in the future. Most of the build happened during my master's studies, so I tried to keep it on a budget wherever I could. I think the setup which it is in right now would be around 2,000 euros. This puts the machine in the mid to upper range of a desktop CNC router. You can also get some manual desktop mills for that price, but I don't know how much fun is to work with those. Going with mineral epoxy I think is a cost-effective solution to get a good result. From the overall spending, I think about 800 euros were for structural components, which were the focus of this video. I'm currently working on a follow-up which will go into the control system and the electronics. I will put the cost overview also on this same GitHub repository. All in all, I'm really happy with the project and how it turned out. And see you in the next one.